This is the lecture on Markov chains. The first one, part one, Introduction to Markov chains. So before we go on, I suggest that you brush up on basic probability concepts. I also have a playlist for that, or you can do it on your own using your favorite books, because we're going to be using notation and terminology out of the field of probability. So in this lecture, the lecture outline, we're going to do the definition of a Markov chain. What is it? The Chapman-Kolmogorov equations, and then we're going to go into the classification of states. A stochastic process on a probability space with a natural filtration curly Fn is called a Markov chain if for any subinterval of the reals, the probability that the process xn plus 1 is in that interval, given the whole history of the process, is the same as the conditional probability given only the current state. So that's basically what makes it Markovian, that conditioning on the whole history of the process is equivalent to conditioning only on the sigma algebra generated by the current state of the process. And as we have seen in the definition of conditional expectations and conditional probabilities, this is the same thing as just the conditioning on that random variable, which is probably a notation that most of you will feel more comfortable with and more familiar. So the physical interpretation is that the future evolution of the process depends only on the current state, on the present, and not on the past. And this is why we're also going to see in the literature this type of property referred to as either the Markov property or the memoryless property. The process forgets the past. So the word chain is going to be associated with the fact that the time is discrete in this process, and we call it a chain. So there are two possibilities. The state itself can also be discrete, in which case we call it a discrete Markov chain. And so in the discrete Markov chain, the states are also discrete. There is a denumerable number of states. And we realize that the transition probabilities define matrices. And we will see that the common notation will be matrix notation. Prjn will be the probability that we go to the state j from the state I at the nth time slot or time step. There are different ways of calling that. So that's for a discrete Markov chain. A continuous valued Markov chain, it's still a chain, so the time is discrete, but the states can be continuous. So think, for example, if you're doing some financial modeling or something like that, you're looking at the stock prices from day 1 to day 2 to day 3. So the time is still discrete. You're sampling it in discrete time, but the stock prices can take continuous values. They don't have to be integers. So in those cases, we are going to be using densities. And we talk about the transition kernel rather than calling it a matrix, because it's not a matrix. And so the transition kernel is going to be defined using these densities. So this is a density that is dependent on the little state x. So the value of x, which is of course now a real number. It is not necessarily an integer. If xn is a Markov chain whose transition kernel or probabilities are independent of n, so it means that the dynamics is not changing in time. It's always following the same rule, and we call it a homogeneous Markov chain. Otherwise, we call it non-homogeneous Markov chain. By default, if we don't specify, then by default, it will be a homogeneous Markov chain. And most of the textbooks and the classes that you find are going to assume that the Markov chains are homogeneous. We're certainly going to be talking about homogeneous Markov chains until in our simulation, we find that, well, This course that I'm doing is also a preliminary course for my simulation course, but it is also a preliminary course for the stochastic optimization course. And in both of those other courses, we're going to encounter non-homogeneous Markov chains. But for the moment, we're going to stick to homogeneous ones. This is the first example that comes from the first reference. It's the book by Ross, Introduction to Probability Models. So this is a very simple binary model for weather. If it rains on a day, we say that it's a 1. And if it doesn't rain, we say that it's a 0. So it's a binary, either it rains or it doesn't rain. Now your, basic, your favorite data science guru has done extensive research and has come up with a table. So in this table, it says that if it rained yesterday and it rained today, then the probability of rain tomorrow is 0.7. If it didn't rain yesterday, but it rained today, then the probability of rain tomorrow will be 0.5, and so on. This is the way that we interpret this table. So this is already given. So define the random variable, which is the binary random variable that says xn means it's a 0 if it rains on day n, and it is a 1 if there's no rain on day n. So basically it's telling you whether it's sunny or not. And so the question is for you, just to reflect about it, is xn a Markov chain? Now you can pause the video and think about it before I give you the answer. And so I, strongly suggest you do that because I am going to give you the answer right now. Pause if you want. Okay, so this is not a Markov chain. And this is not a Markov chain, and we can look at that in a very simple way. The information given by xn, for example, if xn is equal to 0, means that there was rain today. So it would be either rain today and rain yesterday, or rain today and no rain yesterday. So the thing is that the information structure that is provided by this random variable, which we call, of course, the sigma algebra of this random variable, does not contain enough information in order to determine uniquely what is the probability of rain for tomorrow. So it doesn't have enough information for that, because knowing only that it didn't rain today, or sorry, that it rained today is not enough to know whether it will rain tomorrow or not. So this is not a Markov chain. However, we're going to see now in this example how we can change our data structures, how we can change the variables in order to define a Markov chain that will describe the process. This is referred to in the literature as Markovianizing. So we can Markovianize some processes by defining the appropriate data structures, and then they become Markov chains. How do we do it? This is the same table as we had before. We now define another random variable. Now, this random variable is going to contain the information from both today and yesterday. So if a 0, 0 means that it didn't, it didn't rain yesterday, it didn't rain today. And so we call that state 0. And then there's obviously 4 possible combinations of the yesterday and today variables. And so there are 4 states for our new random variable yn. It turns out that, of course, if yn is the pair 0, 0, then the yn plus 1 cannot be any one of those. If we are looking at this particular outcome, this particular outcome would say that for the yn, we had rain yesterday and rain today. So that's the state 0, 0. Now, where can we go from here? What would be yn plus 1? Well, yn plus 1 is asking about today and tomorrow. So if today already has a check mark, then the only possible yn plus 1 will be either we stay with rain and rain, or we go into rain and no rain. These the other states are not possible. So we cannot go from this state to that one because there will be a contradiction. You see, when we go from n to n plus 1, what was today in step n becomes yesterday in step n plus 1. So this would be an inconsistency. So anyways, I'll let you work it out, or you can take a look at the reference and see how this is resolved. And so we can write a transition matrix for the probabilities of the yn plus 1 given yn. And now we have 4 states. Instead of having a binary, we have 4 states. Now, this is a very simple example, but it illustrates a very, very important method and a very important observation. When we want to program something on a computer, the only thing that we can do is program Markov chains. The computer cannot deal with anything else. Why? Because if you're doing a code and it turns out that you need something from the past, then the right way to do is to keep those values that we're going to need from the past, keep them in memory. So what this amounts to is to do pretty much the same thing that we're doing now with the rain example, is that we enlarge the state. So our data structures have to consider some variables that are going to keep the memory from the past if you need it. And so this is very important because, again, in the simulation course, we're going to be Markovianizing the processes so that we can work with an appropriate Markov chain. This is an example that I use in my classes. This is actually one assignment, one question for the assignment. Well, this is not the question, this is just a model. So this is the rat is in a labyrinth. And the labyrinth has he starts on a chamber, which is the chamber that is marked in like a muddy color. And the chamber has 2 openings, basically it's either the green one or the yellow one. So Theseus is going to choose either one of these 2 openings with probability 1/2, so equally likely. If he goes to the right, which is the yellow path, then after a 3-minute walk, he's going to come back to the initial chamber where he was. If he chooses left, after 1 minute, the path is bifurcating and it becomes, it's either going to continue on the green path or he's going to go on the blue path. With probability 1/3, he's going to go to upwards towards the exit. After 1 minute, he finds the exit. So done. But with probability 2/3, he chooses the downward path, which is the one that I drew in blue. And this one actually brings him back to the original chamber. So that's the way that Theseus the rat is going to be walking around the labyrinth. So the exercise for you. Is the walk by Theseus the rat represented by a Markov chain? And if so, what is Xn? So it's an exercise for you to start modeling. The second one has to do with the game of craps. You can look it up in the website or in the books that I refer to, the textbooks. Is the game of craps represented by a Markov chain? And if so, what is Xn? So you pause and you can pretty much take your time to solve these problems.
This is a very important tool for calculation, and it's called the law of total probability. What it tells us is that the probability of an event can be calculated by condition. First of all, we define a partition of the set omega. A partition, as I might recall, is a collection of disjoint sets whose union is the whole of omega. So that's a partition. And for any event E, the law of total probability tells us that the probability of that event can be calculated as the sum of probabilities which are conditional on each of these sets. And when we translate that into expectations, we can also calculate expectations using the law of total probability. And we're going to be using this quite a lot. So you should keep that in the back of your minds. So we're going to see now the second topic, Chapman-Kolmogorov equations. For a homogeneous discrete Markov chain, these quantities Pj superindex m, which are the probability that xn plus m equals j given xn equals I, are called the m-step transition probabilities, because going from step n to a step n plus m, we need m time slots, and those are called steps usually. And so the theorem tells us that the probability that the Pijn, so the n-step probability, can be computed in terms of the n-1 transition probability. If you're working on computer science or you're working on mathematical logic, these Chapman-Kolmogorov equations are basically a recursion. So they work on recursively applying the same concepts for a smaller step. So we're going to see now a visualization of how this works. So in order to see this, we're going to use my iPad. And what we do is the following. We want to prove this equation, which is the equation that tells us that this is the way that the transition probabilities behave. So it's a recursion on the probabilities. So the key to prove this, or to understand why this is true, is to use the law of total probability. So the law of total probability told us to take a partition of the whole omega. The partition will be the following. We start here at state I. So then let's say that this is the first step that we're going, the first state. So this is happening at time 0, let's say. And then we are going to land, or we want to know what is the probability of landing at state J. So let's put this state, say, in yellow. So we want to know, how do we go from state I into state J? And we want to count all of the possible ways that we do that. So to do that, we know that there has to be one step. So we're basically here, we are counting, right, n steps. Why are we counting n steps? Because we are asking for this quantity, the probability that starting at I and moving n steps, I end up with at the state J. So the partition that we're going to do is that we say, well, at the very first step, there has to be one state. We don't know which one, but there has to be at least one state. So we take all of the possible states. Of course, I can't draw it if it's an infinite number, but we assume that, it doesn't really, you can just visualize it. So we say that there is an intermediate state. What is the intermediate state? Well, I'm going to label this intermediate state with a K. I'm going to say K is any state in the whole state space. The state space is, basically the natural numbers plus 0. So I am going to take a look at the intermediate states, and I'm going to say that in order to go in n steps from I to J, I must have gone to at least one of these states the first time. And this is also called the first step analysis, particularly in the Carlin and Taylor book. So this is also called first step analysis. It's conditioning on the first step. And so if I condition on the first step, and then of course we need to figure out after conditioning on that step, then we go from that state K, we're going to go to J, but now we're going to go in n-1 steps. So if these were n steps, then from here to there will be n-1 steps. So how do we do this? We say Pijn, using the law of total probability, will be, well, first of all, I'm going to write down exactly what it is. This is the probability that x n plus 1 is equal to J, given that I started at the first transition with state I. So there are n steps in here. And this is going to be equal to, and this is the law of total probability, I am going to add up over conditioning on all the possible intermediate steps, that is the state K, where the process lands after just one step. So this is the sum over all the possible intermediate green states that I put in there of what? Well, this will be the probability that x n plus 1 equals J. And now I'm conditioning not just on x1, but I'm going to condition also on x2. I do one step. So this means that I'm conditioning on x2 as well. And then I have to multiply by the probability of the conditioning event. So the probability of that conditioning event is the probability that x2 is equal to K, given x1 equals Notice that I'm carrying that conditioning. So I'm carrying this conditioning on the on the state that I started. So this is a conditional probability. And as we saw in the first set of in the first playlist or the first set of lectures, a conditional probability, when you condition on a particular state I, it is a probability. So this has to be carried out all the time. So it's a conditional probability. It's related to what we're doing. We're conditioning. It's a conditional probability is a probability, and so we treat it as an integral term. So that's why we keep the information on the original conditioning. All right. So what is this quantity? This quantity here, just by definition, is just the probability P that I go from I to K in how many steps? In one step, because it's going from 1 to 2 time steps. So this is just P I K. And let's take a look at the other one. The probability that xn plus 1 is equal to j, given x1 equals I and x2 equals k. Now we use the Markovian property. The Markovian property tells us that if we condition on the past, on all the past, then it is the same as conditioning only on the present. So basically, what it's telling us is that this term here can be it is memoryless, so it's forgotten by the Markov chain. It doesn't change the calculation. So this is exactly the same thing as just conditioning on x2. So this is xn plus 1 equals j, given x2 equals k. And now we say, well, going from 2 into n minus 1 requires n minus 1 steps. And so this will be equal to p kj, but now in n minus 1 steps. So when we put everything together from this formula here, what we obtain is that pijn will be equal to the sum of from k equals 0 up to infinity of p kj n minus 1 and then p pij. And this is, of course, the same that we wanted to prove. And so that is the proof of the Chapman-Kolmogorov equations. So once we've seen the Chapman-Kolmogorov equations, what we realize is that the algebra to calculate the transition probabilities of a Markov chain corresponds to the regular matrix algebra. So we can treat the transition probabilities as regular matrix and regular matrix multiplication, which is very useful. We're going to go now into the third topic of this lecture, and that's the classification of states. So if we have a Markov chain with a state space, which is a discrete state space, we say that state J is accessible from state I if, and the way that I read this, so the interpretation of this, if, what it says, if for, given sufficient amount of time, there is a positive probability of going from state I to state J. So that's the notion of the accessibility. So we say that J is accessible from I if, given a sufficient amount of steps, there is a positive probability that we go from I to J. Now, the second definition is the definition of communication. It's a relation between the different states in the state space. We say that states I and J communicate if J is accessible from I and I is also accessible from J. And we write it with the double arrow. And what is very interesting is that communication is an equivalence relationship. For the proof, you can take a look at the first reference in Ross. But now we're going to be working with an example on trying to get a little bit of an inkling of how do we visualize communication between different states. For this, we're going to do a very, very small, simple example, but it will be introducing the way that we actually visualize Markov chains and the way that we use all these different diagrams. So if you already know this, of course, you can go very fast. But if this is the first time that you're looking at this, then I hope that this is going to be quite useful. So what we're going to do now is the following. This is a probability matrix for a Markov chain that lives in a very small space. It has only 4 possible states. So in what way can we visualize this transition probability matrix or this Markov chain, this process, is the following. We look at each of the rows, and the interpretation is that this is telling me that the probability of going from state 1 into state 1 is 0. The probability of going from 1 to 2 is 8. From 1 to 3 is 0.2. And from 1 to 4 is 0. So that's the way that we interpret the rows. So the rows is like the initial state, and in one step, it tells us, the column is telling us the probability of going into the other ones. So we can actually we can actually visualize this. So from 1, we cannot go to 1, but we could go to 2. So we put an arrow here. And, it's useful to write down here the probability of going into there. And to go to 3, we have another, it's possible as well, and this is 0.2. Notice that by construction, from state 1, we can only just go to any of the other states. So the sum of all the outgoing links is going to add up to 1. You can look at this also as a flow network. Okay, so from state 2, we can, it says that we can stay in state 2. So with probability 0.9, we stay in this state, or the Markov chain stays in this state. And with probability 0.1, it can go to state 4. So it goes directly to state 4. And this will be 0.1. And again, the sum of 0.9 and 0.1 is equal to 1. And then from state 3, we can go to, we don't go to 1, we can go to either state 2. So we can go here, and we go to state 2 with probability 0.5, or we can go to state 4. And we go with the probability 0.5. And then from state 4, what happens in state 4 is that we go with probability 1, with probability 1, we go to state 1. So there's an arrow over here. And this is probability 1. Okay, so how can we visualize communication? So the way to visualize communication, I believe it's a lot easier when you look at this diagram. So these are the diagrams that contain the same information as the matrix, but I believe it's a lot easier to figure things out. So for example, our state 1 and 4 communicating. Well, communication, so I'm asking if 1 communicates with 4. That's the question. And evidently, we do know that 1 is accessible from 4, which we can read directly from this arrow. We can go to state 1 in one step, but can we go from 1 to 4 with a positive probability? And the trick of using also the Chapman-Kolmogorov equations is that we realize that the probability of going from state 1 to state 2 and then to 4 is actually the multiplication of these probabilities. So with probability 0.8, we go to 2. And then further with probability 0.1, we reach 4. That's a positive probability. So indeed, there is at least one way in which we can go. Of course, there are other ways. We could go through 3 and then to 5 and so on. So we can also go from 1 into 4. So it means that, yes, these two states communicate. So what happens with all the other states? Are states 3 and 4 communicating? Well, we can go from 3 to 4. And by the same token, we can say, oh, yeah, well, from 3, we can go to 4. And then from 4, we can also go to 3, because from 4, we go to 1. And then from 1, we can go to 3. I'm not going to do everything because it would be a little bit boring as well for this video. But you can pretty much realize that in this particular case, all of the states are communicating. So let me just, for fun, let's just change very slightly, just very, very slightly. We can go back to the same thing afterwards. What happens if I, instead of going to 4, from 4 to 1, I had this diagram? I just changed one arrow. Is this changing a lot? So what happens now with 1 to 4? Well, 4 is still accessible from 1 because we can take the routes that we mentioned before. But is 1 accessible from 4? Well, we could go from 4 to 3. Actually, we can only just go to 3. From 3, we could go to 2 or to 4 again. But if we go to 2, there's no arrow pointing back to 1. So in this diagram, as simple as it is, I'm changing just a tiny, tiny little thing. It turns out that 1 is not accessible from state 4. So what this means is that in this case, not all states communicate with each other. So now we are going to have to figure out which are the states that do communicate with each other. So we start looking at that. Well, are 2 and 3 communicating with each other? Is it possible to go from 2 to 3 and from 3 to 2? Yes. So 2 and 3 do communicate. Are 2 and 4 communicating? Yes, it turns out that 4 and 2 are also communicating. So in this case, we got 2, 3, and 4 do communicate amongst each other, but 1 is sort of on its own. 1 has been left to bend for itself. So that's basically what I wanted to do right now. Let's go back to the lecture. So after the example, we know that communication is usually much easier to visualize when we use the diagrams and what that means. We can take a look at Markov chains in terms like a flow network and things like that. And of course, what is flowing is basically the probability, but that's another topic. Okay, so what the very important result is that communication is an equivalence relationship. So what was an equivalence relationship? Perhaps you want to take a look at that on your own, but I just wanted to mention an equivalence relation in a set partitions the set into disjoint classes. And therefore, for the topic that it occupies us today, all states that communicate belong to the same class. And this is why this topic is called classification of Markov chains. So for the moment, we're just classifying the state of a Markov chain. A finite Markov chain is characterized by a transition probability matrix. Finite meaning it lives on a finite discrete state space. So now we have a regular transition probability matrix. And when we use diagrams, if there is a finite number of states, there's a plane overflying there. So we have a finite number of states that we look at the nodes, and these diagrams are an alternative way of expressing the same probability matrix, but it helps us to visualize the flows and the communication in particular. Now, in order to determine, in the example that we did, in order to determine whether 2 states communicated, we just basically needed to see whether there were arrows going, building the paths from one to the other. And it doesn't really depend on the actual value on that link. Diagrams are structured. The diagrams are telling us what is the basic structure. Communication and classes are independent of the numerical value of these entries. They're only dependent whether they are positive or 0. And this is going to be very interesting. And this is going to be very important when we look at Markov chains in general. So now we know that because communication is an equivalence relationship, it induces a classification. It induces a partition where we're going to have a certain number of classes only. And all of the states belong to one class. And the states that communicate belong to the same class. So what are the classes? So this is the definition of the classes. First, we look at the following quantity. The first return time to the initial state is defined as a random stopping time adapted to the Markov chain, as we've seen in the basic probability chapters. And the following definition is important. The probability that the first return time to state I happens at time n or step n is denoted by f sub I superscript n. So this is basically just the probability that this first return time is equal to n. The probability that a process eventually returns. So we're saying we don't know when. We're not specifying the time step, but eventually is obviously the sum of the probability that the first return is on the first time step, or that the first return is on the second, or on the third, or the fourth, and so on. So this is the basic definition of a probability that is the sum of the probability of disjoint events. And of course, these disjoint events is the event of when was the first return. So now we're ready for the definition of the classes in a Markov chain. A state of a discrete Markov chain is called recurrent if fi is equal to 1. So the probability of coming back is equal to 1. Furthermore, a recurrent state is called absorbing if PII is equal to 1. So if being on the state I, there's nowhere else to go but state I, that is called absorbing. And of course, if you're looking at this in terms of flow networks, this would mean that we have there the terminating or sink node. We say that a state is positive recurrent if I is equal to 1 and the expected value of the first return time is finite. And we say that the state is transient if the probability of eventually returning is not equal to 1, but it's smaller than 1. And there is an important theorem that tells us that recurrence is a class property. So again, if we have one state that is recurrent and we know which are all the states that communicate with that one, then all of the states that communicate with it are also going to be recurrent. So we're going to go back to our examples and analyze what happens in the two hypothetical cases. The scenario 1 is the one that I drew now with a yellow arrow. And in this scenario 1, we know that all of the states communicate. So in the yellow scenario, so scenario 1, it means that the link is from 4 to 1. So going from 4, and it's the one that actually reflects this particular transition matrix. So in this scenario 1, we have already seen in the exercise before that all states communicate. What this means is that, the probability of going back to this a particular state is always going to be positive. So we're always going to have the probability of coming back to any state as, eventually coming back as being equal to 1. So what this means is that all of the states are recurrent. Of course, you can also look at mathematical proofs, very rigorous proofs of this result, that when you have a finite state Markov chain and all of the states communicate, then all of them have to be recurrent. So this is a general result. So let's take a look at the scenario number 2. So what happens in scenario number 2? So in this scenario number 2, we have that state 1 is transient. The probability of coming back to state 1 is actually 0 in this particular case. So it's relatively easy to see that that would be transient. And just so that we don't confuse things, in this particular case, I put this probability became 0. So in this case, this will be 0.0. And the probability, so that you know what we're talking about, and the probability of going to 3, is equal to 1. So we basically swapped one link. Instead of going to 1, we're going to 3. So that's reflected in that probability. So in this case, state 1 is transient. All the other states are recurrent. They communicate with each other. And all of the other states are recurrent. Let's take a look at a further scenario. So this will be the last one that I want to talk about. In this scenario, we basically are going to say that once we attain 4, we're going to attain that with probability 1. So we're no longer considering the green or the yellow scenario. And so in this particular case, the red scenario, what happens here? Well, what happens in this case is that the state 1, it is still transient. Once we leave, after the first time step, there's no way to come back. So 1 is also transient. Oops. But what happens with the communication? Now, is 3 and 4 communicating? So let's see, are 2 and 3 communicating? Well, I can see that there's a way to go from 3 to 2, even with probability 0.5, but there's no longer a probability that I can reach 3 from state 2. So now they're not communicating. And what is happening with 3 and 4 or 2 and 4 is the same thing, because now the only state, so 2 will be transient. The moment that from state 2 we go into state 4, we never come back to 2. And it turns out that 3 is transient as well. So very small changes. very small changes in the structure. And it really changes completely the way that the Markov chain behaves. And what is 4? Well, 4 is not just recurrent, but it is an absorbing state. So this is absorbent. So in particular, this will be recurrent. So this small example can help us visualize what happens in general with the classification of. It is very important to know what the what is the structure of the Markov chains. It is related as well to matrix algebra. If the matrix is irreducible, then it is equivalent to what we were saying. There's only one class. All of the states communicate. So if you're familiar with matrix algebra, you can just take a look at that. You know that matrices that are not irreducible usually can be divided into block matrices. And so all of these block matrices will correspond to classes, and the states within those block messages, I'm talking about the probability, the transition probability matrix, and all of those states would be communicating. It's important to know whether we have absorbent states or not. As I mentioned, a state is called absorbing if the probability is equal to 1. And what we're going to see is that the study of Markov chains is basically going to be roughly studying either irreducible chains, and we're going to be talking about the long-term behavior when the probability mass is telling us where the chain, the dynamics of the chain is coming back to certain states and staying and then going and returning. So we're going to be talking about the long-term Markov chain study and the study of absorption. So the very famous absorption example is called the gambler's ruin problem. And it's when you can have either the gambler wins the bank, wins the whole money in the bank, or the opponent wins everything and he loses. So there are two absorbing states from the point of view of a gambler, and the gambler would either lose everything or win everything. And so it's important for the gambler to know what is the probability of one or the other. Now, absorbing probabilities, of course, are very useful to study many other things and not just gambling.
Sorry about that. There's really no exercise at the end of this lecture. This is the end of the lecture, and the next time we're going to see Poisson processes, which are going to get us ready in order to see continuous time Markov chains, which is going to be the third module. And thank you very much for your attention.